setup. Brilliant. And he will be talking to us about the effects of spatial non-uniformity of heterogeneous excitable bursters on coordinated activity in a diffusively coupled lattice. Danny, please, you have the floor.
Okay, hello. Thank you for coming to my talk, and welcome to my flat. Yes, so I'm going to talk about this spatial non-uniformity in these bursting networks. But first, I would like to thank my collaborators. So I work at the University of Birmingham, and, the medical school. I work at the Institute of Metabolism and Systems Research, where I work with Professor David Hodson, who is a experimentalist. His focus is on beta cell networks, which are pancreatic insulin secreting cells, and its relationship to diabetes. I also work with a quantitative group, the Center for Systems Modeling and Quantitative Biomedicine, where I work with John Terry and Isabella and Carol Breen, and as well at the University of Exeter with Kyle Wedgwood. And I couldn't have done this work without them, so many thanks. Okay, so the first I'm going to talk about the motivation for this problem, which is a biological motivation. I'll talk about the mathematical model we're going to look at of single cells and the heterogeneity that we want to include in these single cell models, and then we will couple them into a network and study the spatial non-uniformity of that network. Okay, so the motivation for this work comes from the pancreas, actually. So it's not specifically a neuroscientific question. And the pancreas is, among other things, responsible for maintaining glucose homeostasis throughout the body. So it contains these populations, these networks of electrically excitable and diffusively coupled cells called beta cells, which take in glucose and convert it into ATP. And that ATP will close some potassium channels that activate the cells electrically, and they begin to burst. And these bursts will increase the intrinsic levels of calcium within the cells, which causes insulin secretion. And they do this in a highly synchronized and coordinated manner. And so I have a couple images here. So on the right, you can see some staining for beta cell networks within a pancreatic islet, and there's different markers for them. So insulin is the one that is most clear. So that's the actual glucose regulating hormone. And then also what you can see in the bottom left is for example, the calcium activity of an islet, which is a good readout for the insulin secretion of an islet. And so at the top, you have the average over the whole islet. And then below that, we have 88 or so recorded cells. And you can kind of see this high level of synchronization of the calcium dynamics. And for a long time, the way this has been studied due to technological constraints, as well as the way these things are coupled with these diffusive coupling, it was thought that you could kind of just look at the average over the whole islet and consider what that's doing over time. And so the mathematical models of a beta cell were kind of tuned to the activity of a full islet. And this led to many, many very important studies and findings. However, more recently, there have been several experiments using multicellular calcium imaging. So this is looking at the calcium activity of single beta cells and groups of single beta cells within an islet, and as well the ability to genetically manipulate or excite or inhibit single cells or target single cells or groups of single cells within the islet. Has made a lot of progress recently. And so what's been found to a high degree is actually that while these things do synchronize, heterogeneity in function and heterogeneity in the genetic profiles of the cells within the islets is actually crucial to the proper functioning of the islet. And so we're going to take a look at one example, and this will be the direct motivation for what I've been working on. So in this experiment, what they were doing was they were looking at a cross-section of an islet. You can see that in the experimental image. And what they were doing was they were looking at all of the cells. So they're doing multicellular calcium imaging again. And what they found is that so they looked at individual cells, and they also looked at the quadrants of the cross section of the islet, so the 4 quadrants. And what they found was that the different quadrants displayed different levels of metabolic activity. So that's how much ATP is produced in response to glucose. And this can be thought of as a proxy for excitability as well in the cells. And what they found was the different quadrants had different levels of metabolic activity. And this was actually related to, in a sense, how much they control the islet. So what they would do is excite these quadrants or excite these single cells and then see to what extent the rest of the islet was actually excited. So in some cases, they would excite a quadrant and the whole islet would be excited, or in other cases, they excite a quadrant and only a small portion of the islet is excited. And then, and so this was all experimental work, but they also put this into a mathematical model, which you can see on the right, where they took a spherical shaped islet and they took 4 sections of the islet and gave them variable metabolic activity. So this was each individual node was a beta cell model. And then they found that they were able to reproduce some of the experimental findings. And it was very interesting. But the reason we wanted to kind of probe into this further is because this was kind of a very narrow study. So it really only works given the experimental constraints. And additionally, the idea that actually what's happening is that we have 4 separate subpopulations of cells in the 4 corners of the islet was never actually what anyone really expected to see. And so what I was trying to do was look at this spatial non-uniformity and try to do it in a more generalized way with a beta cell model, but a simpler beta cell model that's really just a model of a bursting cell. Okay, so the mathematical model for a single cell we're going to use is an early conductance-based model of the pancreatic beta cell. It's a lot like a Hodgkin-Huxley type formulation. So it's got fast hyperpolarizing potassium channels and calcium channels, which lead to the calcium channels depolarizing, and these cause the fast spikes. So this is similar to the sodium and potassium in the Hodgkin-Huxley model. But it also has calcium-dependent potassium channels, which will lead to bursting. So these things so calcium slowly builds up within the cell, which opens up these hyperpolarizing potassium channels and leads to termination of bursts. And so you have this bursting activity, and that bursting activity is what leads to the pulsatile insulin secretion in islets. And then we also have some leak channels, which is going to set the excitability of the cells, and I'll talk a little bit more about that. And then also we have diffusive coupling in this model. Okay, so in this model, we're actually using a leak channel as a kind of simple proxy for these K-ATP channel, these hyperpolarizing ATP sensitive channels. And the idea is that normally the mathematical models of these K-ATP channels would have an ATP variable, and ATP varies really, really slowly, but it does change the dynamics somewhat of the model. But we thought that for simplicity, and because the dynamics are so slow, what we could do is actually just have a leak channel and this single parameter G, which is essentially a fixed ATP or a fixed glucose value. And so this is going to set the network activation, and it's a global parameter. So all the cells in a single network will have the same activation, the same glucose level, you could think of it as. And then also the max conductance of the leak channel is going to set the excitability. This will be a local parameter, so cells will have different values, and this is going to be one of the places we include heterogeneity. So the heterogeneity will be in cell excitability throughout the network. So here's just a simple example. So for G at some level of activation, this is kind of a high activation. For different leak values, you can see the bursting. So for example, in red, this is kind of a very excitable cell. So it has a high mean calcium and a high oscillation frequency. And then as G sub L increases, as the leak current increases, what you see is lower mean calcium as well as slower oscillations. And then for G sub L past some value, you reach a phase transition where you have just quiescence. And Okay, and then we also have these coupled cells via gap junctions, which is just some max conductance of the gap junction, and then it's the difference between the voltages of the two cells, and these things are symmetric. So if cell I is connected to cell J, then cell J is connected to cell I, and we couple these in a network which has the following architecture. So it's a 3D network which uses hexagonal close packing of equally sized spheres to form a lattice. So that's shown here on the bottom left. So here we have a central node, and it has 12 nearest neighbors, and it shows all of their connections. So each node in the interior of the lattice will have 12 connections. And then the full network, an example of a full network can be seen on the bottom right. And it just forms a sort of sphere. So we embed the hexagonal lattice within a sphere of about 1,000 oscillators, which is the order of magnitude of a pancreatic islet. Okay, so heterogeneity and spatial non-uniformity. So the way we're going to do this heterogeneity is we're going to consider two populations, and this is motivated more or less by the islet studies, so the levels of more excitable and less excitable cells within the islet study. So we have a population 1, which is about 10 to 20% of the islet, and it's more excitable. So these are at the levels of activation, network activation that we look at. These things are intrinsically active, you know, if they don't have gap junction connections, whereas population 2 is less excitable, and within the network activation range that we look at, these would be intrinsically quiescent and then make up like 80 to 90% of the islets. And then we start with a spatially uniform distribution. So we just randomly plop down some of these blue population 1 cells throughout the islet, but it's completely uniformly distributed. And what we did was we generated an algorithm that could create spatial uniformity. So here I've got 5 examples where each column is an example of transitioning from complete spatial uniformity to spatial non-uniformity. And so we choose some different configurations of the spatially uniform network, and we do some algorithm, and over several iterations, you can see, if, for example, in the second row, the things are starting to clump. Population 1 cells are starting to clump up, and then they clump a little more in row 3. Row 4, they're getting quite clustered. And then at the end state, you generally have 1 large cluster or maybe 2, and in some cases 3. And so so first I need to define a measure of spatial assortativity, which is just going to be the measure of the tendency of members of the same population to be connected to one another. And we're using the name spatial because the nodes are forming connections to their nearest neighbors. This is similar to the network science definition of assortativity, for example, degree assortativity, except that the preferential attachment is about an intrinsic property of the node rather than, for example, checking how likely 2 nodes are with similar degrees to be connected to each other. So it's not a property of the network, rather a property of the intrinsic properties of the node. And so the way we define this then is we have sort of 3 separate definitions. First, node assortativity, which is just the fraction of connections onto nodes from the same population. So here I've got population 1 in blue, population 2 in red. If we look at population 1, node 2, you can see it has 3 connections, and 2 of them are onto population 2. So the node assortativity for A sub 2 would be 1/3. And then the population assortativity is the mean node assortativity across a single population. So population 1 will have its own assortativity, and population 2 will have another assortativity. And then the network assortativity is the mean of all the population assortativities. And what this does is that it prevents biasing of the assortativity based on the size of the population. So if we have one small population, they are sort of equally weighted in the assortativity measure. So then we have this algorithm, which I can only talk about the kind of bare bones. There are some other details that are pretty interesting, but you know, if you're curious, feel free to ask. And so basically we have And on each iteration, what we do is we select a pair of nodes, one from each population. So in this case, for example, we could select population 2 node 1 and population 1 node 3. And the question is, if I swap them, does this increase that network assortativity? And if it does, then I will accept the swap and I will move on to the next iteration. And if it doesn't increase this assortativity, then just reject the swap and try a different pair of nodes. And if all pairs are rejected, that means that no further improvements to spatial assortativity can be made. So we terminate the algorithm. So it'll be somewhere on the order of 300, 350 iterations for 10% population 1 until you reach that sort of clustered state that we saw earlier. So here's an example over one of the networks. So starting from just some uniformly random distribution, what you can see is that one sort of large cluster appears to be forming in the center, and the assortativity is monotonically increases due to the way that we wrote the algorithm. And then in the final state, what you have is a single cluster of cells sort of in the center, and this is the maximal spatial assortativity that you can have given the initial condition and the ordering of the swaps that occurred. Okay, so there we go. Okay, and so now we're going to put some network dynamics onto this, onto these spatially non-uniform networks and see what happens. And just a reminder, so we have our global activation parameter G, which is in 0 to 1. 0 means the network should be fully inactive. 1 means that the network should be fully active. We have network assortativity, which is also in 0 to 1. 0 means completely uniform random distribution of the two populations of cells. Practically, this can only go to about 0.7 because 1 would actually mean that you have two disjoint populations. And since all of the cells will be connected to each other in one way or another, this is the sort of in practice maximum. We're also going to look at various coupling strengths. So 1, 2, and 10 is just weak, some middling value, and then a strong coupling strength. And then we've got have our local parameter of node excitability, where population 1 is more excitable. Okay, so here's just one example I'm going to give where I'm looking at the network starting from the uniform random case and going to the clustered case. And what we're looking at on the right is various mean calcium traces for different levels of activation. So the main important thing to remember is that the top panels are higher network activation. So that you could think of that as more glucose, so more bursting. And then the blue curve is the mean calcium of population 1, and the black curve is the mean calcium of population 2. And then I just have 10 traces. And at this point, they're all quiet, even so you have actually no activity when things are uniformly distributed. But as we start to introduce non-uniform distributions, what you can see is that as this thing becomes more and more non-uniform, you start to see activation for lower and lower levels of G, of the network activation parameter. And so this thing becomes essentially more excitable, which perhaps makes sense as this population 1 cluster is the more excitable population, and they are sort of becoming somewhat of a supercell. Okay. So this is another way of looking at it. So what we're really interested in finding is phase transitions with respect to this non-uniformity. So we have increasing the activation parameter G. Of course, this will lead to a phase transition as when it's 0, it's always quiet, and when it's 1, it will always have some activity. And at some point, you'll go from a quiet system to a loud system. But what's interesting is as you increase assortativity, but don't increase this network activation, you can also see a phase transition. So for example, for low G, it takes a high degree of assortativity, of spatial assortativity, whereas for higher values of G, it takes a lower change in assortativity to get the phase transition. And so what we're going to do is actually look at several different networks in assortativity and network activation space on a Latin hypercube, run the dynamical system, and then assess the network measures at each point. And the network measures we're going to look at is the mean calcium peaks, which is the average number of bursts over all the nodes. So this gives us an idea of the frequency of activity in the cell network. And then we're also going to use the Kuramoto order parameter to measure the synchronization of the islets or the cell network. And just a quick reminder of the Kuramoto order parameter, what it is. So supposing you have two time series, in this case, I'm using sine waves in the top left. Over time, you can see that the values will change, and sometimes these things will be close to each other, other times further. So what we do is a Hilbert transform, and that gives you the top right, where you have, with sine waves, you just have two circles with the amplitude given by the amplitude of the sine waves. And the question is, how synchronized are these? And so what we do is we project these onto the unit circle. So that's on the bottom left. And then we add together the values in the complex plane of the two nodes. That gives us a black dot. And the line pointing at the black dot represents the Kuramoto order parameter. So you can see that when the two nodes are far away from each other on the unit circle, the value is small, but when they're close together, the value is large. And then we take the, so that value is all plotted over time on the bottom right, and we just take the average over all times. That's the black dotted line. And so this will be our measure of synchronization. Okay. And so we were looking at the three different coupling strengths, and we have our 2048 points in G and assortativity. And here we're looking at the number of peaks. So that is the average peaks over all of the cells in the network. And all I wanted to say in this slide is that we're then fitting these to sigmoids, and it's kind of the sigmoids that we'll look at. But what you can tell is that for very weak coupling, you have a sigmoid that is not very steep, whereas for stronger coupling, you have a very steep sigmoid. And so it might be easier to actually look at the half maxima of the sigmoids. And so those are drawn here as lines. And what you can see is that for strong coupling strength, what you have is a half maxima that's high value in G, which implies that it takes a high value of network activation to get this system going if the coupling is strong. However, the reliance on assortativity is also strong. So that's given by the slope of the line. So you can see that the slope is very steep and negative because as assortativity increases, the required network activation is much lower. And a similar trend is also true for G coupling in the middle. It does rely, well, assortativity does play a role as well, but it's less defined. And then when G coupling is weak, you can see that the reliance on assortativity is much less. And I should also mention that the thickness of these lines relates to the steepness. And so one interesting thing to keep in mind is that for the middle coupling value that we chose, the steepness of the sigmoid is quite a bit lower than it is for G coupling equals 10. And that's going to be I'm going to mention that again in a second. So with respect to the Kuramoto order parameter, we have very similar results. So for the strong coupling, it takes a lot of activation of G to activate the system, but the relationship between G and assortativity is also quite strong. Although in the coupling case, the relationship between G and assortativity for middling coupling is also quite strong. And also perhaps a little bit stronger for the weak case as well. But one thing I wanted to point out as well here is that what you'll notice for the middle coupling strength is that the sigmoid is also very steep. So for both the middle and the strong coupling strengths, you have a steep sigmoid. And so what that's kind of implying is that for strong coupling, you have a sort of all or nothing activity. So either the network is completely quiet and nothing's going on, or everything is fully synchronized and oscillating at the sort of maximal frequency. Whereas for the middle case, it's interesting. Things do go from no synchronization, no activity, that is, to full synchronization very quickly. However, the actual frequency of the oscillations are much more, are much less steep. So that's basically suggesting that for these middle coupling strengths, you have a stronger dynamic range, which would be kind of very important for the function of the islet, for example, where you really need to know how much glucose is coming in and be able to secrete insulin at a rate that tracks that glucose level. And here's just one other sort of final image, which is just showing the sigmoids as heat maps. And you can see that for the weak coupling, you have sort of a very fuzzy boundary between quiet and activity, and it's less strongly related to assortativity. Whereas for the middling coupling, you have a very steep sigmoid and a pretty strong relationship between assortativity and the activity of the network. And this is shifted up when you have stronger coupling, as the network tends to want to stay more quiet until the activation is quite high. Okay, so a couple other things, some conclusions. We developed this algorithm for introducing spatial non-uniformity into a diffusively coupled network of two populations in this case. For weak coupling, network activity is only weakly dependent on assortativity, but for middle and strong coupling, the network activity is strongly dependent on assortativity. And for the middle coupling, the number of calcium peaks depends more strongly on activation, or G, and so it has a more sensitive dynamic range. And a few future directions. One thing I didn't mention a second ago was with this order parameter, what we're actually noticing for the weak coupling is that synchronization appears to reach some sort of maximum for a middle value of G, and then when G increases further, the synchronization actually decreases. And I have some hunches about why this is, but I'd like to probe that a bit further. We'd also like to demonstrate that these relationships between assortativity and activation, or network activation, are not limited to sort of this bursting model only. Could consider some other models, maybe Kuromoto model, or if it's Nagumo, Hindmarsh-Rose, something like that. And then additionally, we kind of constrained our heterogeneity to keep things as simple as we could, but I'd like to introduce additional heterogeneities into the excitability and the coupling to see how these relationships will change. Okay, so thank you for that. I appreciate your time.
Brilliant. Thank you very much, Danny. We've got time for one quick question.
Oh, sorry.
Cindy, is that a question? At the start of a question, or do you want to unmute? Danielle, can people unmute themselves? Yes, they can.
You mean me?
Yes, yes.
Oh, yes. You talked about the pancreas at the beginning, and I was wondering if you have a connection between your assortativity definitions, which are very appealing, and the function of the pancreas.
Yes, so at the minute, no. At the minute, we're trying to stay relatively data agnostic and just kind of generally look at this relationship of assortativity. What we do know is that in the pancreas, there is this spatial non-uniformity. What we don't have a good way of doing yet is to identify what that spatial non-uniformity actually looks like in the pancreas. And one of the kind of things that would be really interesting to do, and we have thought about ways that we might be able to do this, is to actually gather data to understand sort of, for example, using this assortativity measure to try to assign that to an actual pancreatic islet, for example, and then try to map these results onto experimental findings more closely. But we haven't quite found the way, but we do have the collaborators to do it. So it's really interesting, and we hope that that's one way that we definitely want to go.